So in this chapter, we're going to talk all about counting and different counting techniques. So the first thing I want to talk about are the additive and multiplicative principles. So additive principle, typically this is, or, right? The additive principle states that if an event can occur in M ways, and event B can occur in disjoint ways, then the event of A or B can occur in M plus N different ways. Note, it's important that both events are disjoint, meaning there's no way for for A and B to occur at the same time, right? So if I'm rolling a single dice, there's no way I could roll a 2, and no way I could roll a 3 at the same time. So, at Red's Dogs and Donuts, there are 14 varieties of donuts and 16 types of hot dogs. If you want either a hot dog or a donut, how many varieties do you have? Okay, so I would have 30, right? I'd have 14 plus 16, which is 30. How many two-letter words would start with either A, B, or C? So friendly reminder, a word is just a string of letters. It doesn't even have to be English or pronounceable, okay? Well, there are 26 letters in the English alphabet, so there'd be 26 options for words two-letter words that could start with A, right? Because I would have A, B, A, C, all the way to AZ, and that's 26 different words. The same would be true for B and C. So that gives me 60 plus 18, 78. Now, suppose you are going out for your favorite ice cream. You can pick 6 ice cream flavors and 4 toppings, okay? Now, you can only get one flavor and 1 topping in this example. So how many choices do you have? What we need to do is break up our choices into disjoint events. So let's divide them up by topping, right? So I have 6 ice cream flavors with 1 topping. So we've got toppings A, B, C, D, right? 6 flavors with the second 6 ice cream flavors with the second topping, 6 with the third, and 6 with the fourth. That gives me 24, and we had to make sure that these events were disjoint. The multiplicative principle states that if A can occur in M ways, and each possibility for A occurs in N ways, then the event of A and B can occur in M times N ways. Okay, this can be generalized to way more events than just 2. So why don't we go ahead and work through a few examples. So how many different outfits consist of a coat, and how many different outfits consisting of a coat and a hat can be chosen from 2 coats and 3 hats? So I have 2 times 3, which is 6. That's how I could arrange 2 coats and 3 hats. How many different two-letter words, including nonsense words, can be formed if repetition is allowed? Okay, so I've got 26 choices for the first and 26 for the second, which is 26 squared. So I've got 676 choices. How many different 4-letter words can be formed if repetition is not allowed? Well, we just have to get rid of the repetitive words. Each, remember we have A, B, ... all the way to AZ. So for each letter of the alphabet, there's going to be one opportunity where there's a duplicate word, so we need to take away 26. And that gives me 650 words. So, how many different outfits consisting of a hat, coat, hat, and a scarf can be chosen from 2 coats, 3 hats, and 2 scarves? We're going to multiply these together to get 12 different options. An exam consists of true or false questions. How many ways can you complete the exam, right? So I've got 5 questions. My only options are true or false. So I've got 2 choices for my first answer, 2 for my second, right? True or false. 2 for my third, and so on and so forth. So it'd be 2 times 2 times 2 times 2 times 2, which is 2 to the 5th, 4, 8, 16, 32. Now, if you can elect a club president and vice president in 506 ways, how many members does your club have? So we would have X choices for our president, and then X minus 1 choices for our vice president. So let's go ahead and multiply this together. So I get X squared minus X equals 506. So I need to go ahead and solve this. So I would do that by factoring. X squared minus X minus 506 equals 0. I would factor this into X minus 23 times X plus 22 equals 0, and I'd solve for X. So I'd get that X equals, sorry, that's positive 23 and a, nope, I did that right. So X equals 23 and X equals negative 22. Well, 23 times 22 is 506, so my club has 23 members. Next, I want to talk about counting with sets. So instead of thinking of event A and event B, I want us to think of set A and set B. And these sets will contain all the different ways an event can happen. So suppose you have 9 scarves and 5 hats. How many combinations of scarves and hats can you make? Well, that's scarves and hats, right? So we do 9 times 9 times 5, which is 45. Now, suppose you only need to wear a hat or a scarf, not both. Then how many choices do you have? Well, this is the addition principle, right? We do 9 plus 5, which is 14. But let's look at these scarves and hats as sets. So now we have 2 sets. We have sets S for scarves and H for hats. The set S contains all 9 scarves, so its cardinality, remember cardinality is the size of the set, is 9. And the set H contains all the hats, so its cardinality is 5. If I took the union of scarves and hats, because they're disjoint sets, right? They have no overlap. It would just be 9 plus 5, which is 14, right? Which is what we did on the previous page. So this is the additive principle with sets. So as long as my 2 sets are disjoint, right, then I have that the cardinality of A union B is the cardinality of A plus the cardinality of B. So for the second question, we could think of this, right, as asking how many pairs of X, Y there are. So where X is a scarf and Y is a hat. We'll soon show this is going to be the cardinality of S times the cardinality of H, and we're going to do this by finding the Cartesian product. So given two sets A and B, we can form the set A times B, where A times B is the set of ordered pairs, where X is an element of A and Y is an element of B. And we call A cross B the Cartesian product of A and B. So given two sets, the cardinality of the Cartesian product is the cardinality of A times the cardinality of B. So let's A and B, let A equal the set being with elements A and B be the set with elements C, D, E. So let's go ahead quick and find the Cartesian product. So that's going to equal A with every element in B. So I'd have A comma C, A comma D, and A comma E. Then I would have B comma C, B comma D, and B comma E. So this would be our Cartesian product. As you can see, its size is 6, which is the cardinality of A times the cardinality of B. So now let's talk about the principle of inclusion-exclusion. This is sometimes called PIE or PI. And what this does is this allows us to work with sets when they're not disjoint. So let's F be the set of students taking French and S be the set of students taking Spanish. Suppose we wanted to find the size of F union S. Well, we know the cardinality of F is 16 because it's 9 plus 7, right? We have to include the students who are in French, and that's everything in this blue circle here. And we know the size of the Spanish students is 21. But that's not enough information because we'd have to know the size of the union. So we have to look at our Venn diagram. Here it shows 3 disjoint sets and their cardinalities. It shows F intersect S. That's in the middle. It shows it shows F minus the middle, right? And it shows Spanish minus the middle of what's in both. So now we have F union S equals 9 plus 7 plus 14, which is 30. So what we have to do is we have to take out the intersection because otherwise we would be double counting the students who are in French and Spanish. They would be counting twice. So when it comes to 2 sets, here's our formula. When it comes to 3 sets, things get a little more complicated. So for 3 sets, we have to count all that's in A, all that's in B, and all that's in C. And then what we need to do is we need to subtract where all of these intersect. So here's A intersect C, B intersect C, D intersect C. So subtract that. But that means I've deleted one too many of my A intersect of my middle where all the intersections take place. So I need to add that back in.